Hi, everyone. This is Dr. Grace Estrada. I'm here today to talk to you about the normal distribution and how to do calculations for the normal distribution in our homework 5. So let's go ahead and get started. Okay, so first of all, let's do a recap on what distributions are. So when we have data that we've collected, let's say, for example, we handed out a survey to our class, and we want to know how it is that people feel about completing these calculations. So the choices are maybe it's about how confident you are about doing these calculations, and choice could be strongly agree, neither agree nor disagree, and strongly disagree. Okay, so when we collect the data from your class, what we would like to do is know how often people selected each of those responses. So a distribution really represents how that data is scattered across the different levels of the variables. So the levels would be the disagree and agree component. So a frequency distribution is just a way of visually mapping this information. It helps researchers understand what's going on with their participants. So a frequency distribution indicates the number of individuals who receive each possible response or score on a variable, or receive or actually select. So there are different ways we can visually map this information. We can use pie charts, bar graphs, frequency polygons, or histograms, and it really depends on the scale of measurement that the data represents. So is it nominal, ordinal, interval, or ratio? A pie chart is one of the most common ways that we visually represent information. And what it does is simply depicts the percentage or number of responses. We use this very often for single nominal scale variables. And you will see this a lot in different presentations, whether in applied research reports, maybe articles for the general public. They're very easy to use and easy to understand, which is why they're so common. So for example, if we did a study on how many children were read to at home or not read to, let's say we looked at 60 children, and 48 of the kids said that they were read to at home and 12 said they were not read to. If we were to represent this in the pie chart, we simply choose a different color for each response. So in the example you see here, yellow represents how many children were not read to, and orange represents how many children were read to. As I mentioned before, you can represent the information as either a percentage or proportion, or you can use a raw number of responses. Here, I chose the percentage because it's more meaningful, right? It's more meaningful to say 20% of the kids said they were not read to, whereas 80% of the children said they were read to. This is more meaningful, gives you a better sense that, oh, wow, vast majority of children are actually read to at home. If I just said 48 kids were read to and 12 were not read to, it's not as easy to digest that information. And the whole point to visually mapping this information is to make the data more easier to understand. Okay, another way that we can represent nominal data is using bar graphs. So each bar represents a distinct response. So in this example, those who are not read to are in the blue bar, and those who are not read to are in the green bar. Frequency of the responses is on the y-axis, and you can see it ranges from 0 to 50. And it's, again, a really easy way to represent the information. Notice that the bars are not touching, and this is a big difference between bar graphs and histograms. A frequency polygon, on the other hand, can only be used with quantitative variables. So bar graphs and pie charts you can use for any kind of data. It's most often used for nominal or ordinal data because we're just counting how many times it shows up. Frequency polygon is only for interval or ratio scale data. So the lines represent the distribution of frequency of scores. So in this example, we have had children indicate who prefers their mothers over their fathers, who prefers their fathers over their mothers. So if it's in blue, they selected their mom. If it's in orange, they selected their dad. It's kind of a measure of liking. So one represents, I guess, how much they rated they liked their parents. One represents strongly disagree. 2 is disagree. 3 is neither, kind of neutral. 4 is agree. And 5 is strongly agree. So looking at this example, you can see that generally children rated their mothers higher in terms of liking them than their dads. So we're not going into what that means. We're just giving you an example. So the lines simply represent the distribution of how frequent scores appear. And finally, for a histogram, this is going to be important for our calculations. What we have here is something that's very similar. It looks a little bit like the bar graph, but there's a big difference. For histograms, we are only using it for quantitative variables. So that would be interval or ratio scaled variables. The values of a histogram are continuous. For example, time, maybe weight, things like that. The bars touch, even temperature. So it's important that you interpret these graphs correctly. In a histogram, the x-axis would be kind of the IV, oftentimes that's time, or it could be something like weight, and then the y-axis would be the frequency. The normal distribution is an example of a histogram. So here we go. And we'll talk a lot more about the normal distribution. When we are looking at the distribution shape of a histogram, we really want to look at a few important characteristics. First one is peak. So is there only one peak in the distribution? A peak is a high point in the distribution. What's the highest value? The tail is the end of the distribution. So every histogram shape has 2 tails, right? It has one at the very beginning and one at the very end. We also want to look at the mode. Remember, mode is the most frequent score. So is it unimodal, meaning is there only one distinct peak? Is it bimodal, meaning there are 2 values that often that appear very frequently? We also want to look at the symmetry involved in the distribution shape. So when we talk about symmetry, what we're thinking of is if we drew a line right down the middle, how well do the left and right sides look compared to each other? If they're near mirror images of each other, then we would say it is a symmetrical distribution. So here's an example of a histogram with a bimodal distribution. So you see here, you have occurrence with 0.4 is about the same as 0.8. In this example, with a normal distribution, it's very clear there's only one mode. There is only one peak in this graph compared to this one. Variability is another component that's really important to look at. So when we talk about variability, really, we're talking about standard deviation, right? The standard deviation tells us how spread out the data is from the mean. The further the spread, the larger the standard deviation. If you have a standard deviation of 0, then that means all the scores are exactly the same, right? So keep that in mind. If you have a standard deviation of 0, there is no variability, then that means all the scores are the same. As you can see, you'll have very few scores with really high values, and you're going to have very few scores with really low values. And that's what we mean about the tails. So the low score represents one tail and the high score represents another tail. And there's the mean in the middle. So you can see here from the mean that this is a very symmetrical distribution shape. How does variability affect the shape of a curve? Well, if the standard deviation is really large, you're going to have scores that are very spread out from the mean. So you're going to have probably the mode is not going to be that high, and you're going to see kind of a wide curve. If the standard deviation is small, then the scores are really close to the mean. It means that there wasn't a whole lot of variation in how people selected it. This is what we call a tight curve. If the standard deviation is small, then the scores are very close to the mean. Another component we look at, aside from variability, is skew. So when we talk about skew, that means that the curve is not symmetrical. There's something a little bit off. So if it's negatively skewed, that diagram on the left, the distribution has a relatively long negative tail. What causes this skew would be an extremely low score. So if most of the class, for example, scored 70, 75%, but somebody scored maybe 2, then that very extreme low score would cause the distribution to be negatively skewed. And then you would see a long tail toward the negative component. On the other hand, if the curve is positively skewed, then that means the distribution has a long positive tail, and this would be caused by somebody who has a very high score in our example. So let's say if most people score about 70, 75, and somebody scored 105 with extra credit, then they would cause the distribution to look positively skewed. These really extreme scores are called outliers. So a distribution with a long tail beyond 2 or 3 standard deviations indicates that there is an extreme score. Remember, when we talk about measures of central tendency, we try not to use the mean if we are expecting really extreme scores. Usually then we would use a median or mode, whichever one is more appropriate. But we also always have to be mindful of outliers because they really affect the mean very much. So we want to be careful of that. So let's talk about the normal distribution. When we say something is normally distributed, it means that we are making certain assumptions. So the normal distribution is the most common type of distribution we'll see of all distribution shapes. It is very useful in research because of these assumptions we make and calculations we can do based on those assumptions. So what are they? First of all, if a data set is normally distributed, it is unimodal. That means there's only one distinct peak. Secondly, it's symmetrical about the mean. That means that the mean is right there in the middle of the normal distribution. And most importantly, the values of the mean, median, mode are equal, right? And we have certain characteristics about where the scores fall in a normally distributed data set. So first of all, 68.27% of all scores in a normally distributed data set will fall within 1 standard deviation of the mean. That means you have about a little over 34% will be above the mean by 1 standard deviation, and about 34% will fall of the values will fall below 1 standard deviation below the mean. You have 95.45% of all scores will fall within 2 standard deviations of the mean, and 99.73% of all scores will fall within 3 standard deviations of the mean. That means that when you, without even actually looking at every single data point that you have a really good sense of where those scores fall. So let's take a look at this. We summarize that information about where the data points fall in what we call the 68, 95, 99 rule. So as you can see in this diagram right here, we have in pink is 68.27%, or we round it to 68%. So that means mu is the middle one, or the mean, that in pink, we have 68.27% or 68% of all the data are going to fall within that pink boundary. That's 1 standard deviation above and below the mean. 95.45%, or we round it to 95%, says that 95% of your data will fall within 2 standard deviations of the mean. So if you hear that information, you can guess, where certain numbers lie, certain values, and we'll do that with the calculations. It'll be more clear to you. The 99.7 or 99% rule says that 99, almost 100% of your data will fall within 3 standard deviations of the mean. That's why outliers are values that go beyond 3 standard deviations. And we tend to exclude outliers because they're too extreme. Let's take a look at some of the potential problem sets that you might have. An example of a characteristic that follows the normal distribution are IQ scores. So the mean IQ score of all adults is 100. We have a standard deviation of 15. So if we were to mark off, 100 right there is above the zero, meaning that's the standard, that's the mean. If we were to mark off the values of one standard deviation below, then we would put 85, right? So 100 minus 15, that's one standard deviation, equals 85. Then 100 plus 15 equals 115. And what we now have is a range. We know that approximately 68% of adults will have an IQ score of between 85 and 115. That's what it means. It gives us a really good sense of how the data falls, right? Next, if we look at this, we subtract another 15 from our one standard deviation, and now we have 70. So 85 minus 15 is 70. Then we want to see what's the value of two standard deviations above the mean? Well, 115 plus 15 equals 130. Now, based on our 68, 95, 99 rule, we know that 95% of our values, 95% of adults will have an IQ an IQ score between 70 and 130. Finally, if we were to figure out what are the values of 3 standard deviations below the mean, then we take 70 minus another 15, and that's 55. So our lowest score for the 3 standard deviations is 55. And then we figure out what is the highest score that we would have for 3 standard deviations above the mean, and that's 145. So now we can say 99% or 99.7% of all adults will have an IQ score between 55 and 145. So this understanding of how many values fall within certain numbers, standard deviations of the mean, that's what gives us the ability to solve these problems that you have in your homework set. Let's take a look at the example. So, example normal distribution problem 1. The weights of stray dogs at a particular pound have a mean of 70 pounds with a standard deviation of 2.5 pounds. Assuming the weights follow a normal shape distribution, what weight is 2 standard deviations below the mean? My recommendation when you get these problems is to draw a quick graph. Right in the middle, the mean is 70. Then right away, mark off how many 1, 2, and 3 standard deviations, the values of that would be on below the mean, and then 1, 2, and 3 standard deviations above the mean. And that will really help you solve the problems. So 2 standard deviations below the mean is essentially, we would calculate it as 2 times 2.5. Remember, the standard deviation is 2.5. We want to know what is 2 standard deviations below the mean, so we multiply it by 2. So 70 minus 5, we get 65 pounds. And right there, we've answered the question. What weight is 2 standard deviations below the mean? 65 pounds. So here we have a diagram of it, right? So here you see in blue that marks off the range of one standard deviation, about the mean. And then you have, if you were to mark off the second 2 standard deviations below the mean, you could see right there, the value is 65. So 70 minus 2.5 will give you 1 standard deviation below the mean, and that's 68.5. 70 minus 5, which is 2 standard deviations below the mean, is 65, and that gives you the value of weights 2 standard deviations below the mean. Another problem you might get. Okay, so same idea. You're given a mean, so the mean weight is 70 pounds, and you'll be given the standard deviation. Standard deviation is 2.5. Now it says, assuming the weights follow a normal shape distribution. I always have to indicate that, because if it is not normally shaped, we cannot use the 68, 95, 99% rule. So the question is, the middle 68% of dogs weigh how much? So this question kind of flips it a little. Now, I'm not asking about the specific weight. I'm asking about the proportion of weights that fall within that distribution. So again, if you marked off, like I said you should, where the mean is 70, and then the values of how many 1, 2, and 3 standard deviations are below, and 1, 2, and 3 standard deviations above, you can use this information to indicate how many middle 68% weigh how much. So remember, middle 68% is within 1 standard deviation of the mean. Taking a look at the graph, you know it would fall then within 68.5 and 72.5, because you see it's 1 standard deviation below the mean and 1 standard deviation above the mean. So middle 68% are within 1 standard deviation. 70 minus 2.5 equals 68.5. 70 plus 2.5 equals 72.5. And you can answer between 68.5 and 72.5 pounds. That's the range of weights for the middle 68% of dogs. Okay, last type of problem that I would ask you for the normal distribution. Same information as the first two. Now I'm saying, what percentage of dogs have weights between 62.5 and 77.5? So taking a look at the graph, you can already see 62.5, well, that's 3 standard deviations below, and 77.5, that's 3 standard deviations above. Based on what we know with the 68, 95, 99% rule, we can easily answer that about 99% or 99.7% of dogs have a weight between 62.5 and 77.5 pounds. So those are the 3 main types of problems that I would be asking you about the normal distribution. It might not be about the middle. So I could ask, what weight is 1 standard deviation below the mean and 2 standard deviations above the mean? So you could, what weight range? So 1 standard deviation below would be 68.5. 2 standard deviations above would be 70. So the range would be 68.5 and 75 pounds. Now I could ask you percentages. What percentage of dogs have a weight between these standard deviations, between 68.5 and 75? So you would use your knowledge of the 68, 95, 99% rule to answer that question. So what we're really doing is having a really good understanding of the proportion. So 68%, 95%, 99%, and how that translates into standard deviations about the mean. So hopefully this helped. If you have any questions, please reach out to me, and hope to see you in the office hour. Take care.